exponents. So we're going to be evaluating log expressions. That's going to be converting from exponential form to logarithmic form, and from logarithmic form to exponential form, and just finding out what exactly is a logarithm, right? I mean, we've graphed it in that, but I don't know if we know what it is exactly. And so that's what we're going to figure out, okay, just what exactly is this thing that we call logarithm? Hint, it's an exponent. Okay, so a logarithm is simply an exponent. But let's start, let's go back to, not to them. Let's go, oh, come on, I can't. Let's go back here. So we graphed y equals, let's actually start with y equals 10 to the x. Let's even go back a unit, back to the exponential function. And let's examine y equals 10 to the x in a little more detail. Okay, so let's say we have y equals 10 to the x. And let's make a table of values, x's and y's. And I'm just going to do it horizontally because it takes up less space, right? So when x is negative 3, what's y? What's 10 to the power of negative 3? So you might think, well, okay, so 10 to the negative 3 here, this is my scratch paper over here, right? So like 10 to the negative 3 is 1 over 10 cubed, which is 1 over 1,000. And if x is negative 2, 10 to the negative 2 is 1 over 10 squared, which is 1 over 100. And when x is negative 1, 10 to the negative 1 is, make sure I'll get this, 1/10. What's 10 to the 0? And for that matter, what's anything raised to the power 0? 1. Okay, now remember, in this particular thing here, this is the base, this is the exponent, right? And that the y is the value that you're going to get out of that, right? It's the value you're going to get when you take the base, raise it to the exponent. What's 10 to the 1? Easiest question so far. What's 10 to the power 1? 10. What's 10 squared? 10 to the 2. And what's 10 cubed? Okay, so those are the values we get out of y equals 10 to the x, right? And we could go back and look at the graph and say, okay, yeah, those are the values that we're going to see. I would have to expand it out a lot, right? Because the problem with 10 to the x is it gets really big really fast, right? You go to 1, you're at 10. That's already on the edge of the grid. You go to 2, you're at 100. That's, you know, I mean, our grid only went up to 10, so 100 is like way up there. You go to 3 or 1,000, so it's climbing really fast, right? Let's just take a peek back. Right, so at 1, we're at 10. Well, okay, let me zoom out. Okay, so when it's 1, so now this scale is 1. 1, it's 10. Let me zoom out again, and again, and again, and move it down. Okay, and now we can see a 2, but now this scale's become like, you know, tens and that, right? And so it goes really big, really fast. Let's just go back to what it was. Now, let's graph the inverse function, right? And the inverse function we find by writing it in this form, x equals 10 to the y. So to do the inverse function, we interchange x and y, right? Now, to make this easier to do, I'm going to put in values of y. Right? I'm going to say, okay, if y is negative 3, then what's x? One over 1,000, yeah. If y is negative 2, what's x? 1 over 100. If y is negative 1, what's x? If y is 0, what's x? Y is 1, what's x? 2, 3. There you go. What do you notice about these two tables? They're reversed, right? One has x is -3 and y is 1,000, and that's the way inverses work. They're just reverse of each other, right? If you do a table of values for the inverse, it's just you interchange the x's and y's, right? What did we do in the equation? We interchanged x and y. What do we do in the table? We interchange the x's and the y's. So we've got this function x equals 10 to the y. Okay, I'll let you copy this down, then we'll go here. I'll just pause for a second. So there's the graph of x equals 10 to the y, but we graphed this yesterday. What did we call it? We said y equals log x. And that's the same graph, right? X equals 10 to the y. If I take off the graph y equals x, the orange graph goes away, you get the blue back. So these two things are the same. Okay? And all it is, it's a way of solving this equation, because we generally don't write stuff in the form x equals, right? You can't graph x equals in your calculator, right? Where's the x equals key? It's not as y equals, right? You got this y equals key and you go in and you graph. So x equals 10 to the y is the same as y is equal to log x. Now, there's a base on this log, right? And remember what it is. If it's not written, then it's base 10. And here I did write it just because I want you to see. See this 10 and this 10? They're the same. See this y and this y? They're the same. They're the same thing. And see this x and this x? They're the exact same thing. So when we see y equals log base 10 of x, we can convert that to x equals 10 to the power of 1. When we see x equals 10 to the power of y, we can write that as the log base 10 of x is equal to y. Okay, I'll let you. I won't extend the page. So y equals log x is read as the log, that's right, is read as y is equal to the log base 10 of x. Okay, so when you see log base 10x, it's read log base 10x. Sorry, I can't read it differently than it is, right? When you see this expression, right? If you don't see a log, if you don't see a base, what's the base? 10. And it's known as the common logarithm because it's used a lot. And it's the log key on your calculator, right? Is a base 10 log. So if I write y is equal to the log of 100, then what do you do? So you say, so what is y? Let's go back a page and down. In here, what's y in this expression? What's the name for y, where it is? It's the exponent. And when it's over here, it's still the exponent, right? So the y value in a log expression is the exponent. What exponent? Well, it's the exponent that you take the base 10 and raise it to this exponent to get the value of x. Or in other words, 10 to the y equals x. Okay? So if you see it written as a log, you can convert it to an exponent. Okay? The base is the same, right? Whatever base is there. Because we're not always going to do base 10. Right? We'll look at base 2 in a minute. Okay, we can do base 2. But the y value, right, y, so here, y is an exponent. So that's all a logarithm is, right? Somebody says to you, oh, you're doing logs. That's just an exponent, right? I think you're doing logs before the 30-1s do logs. So, you know, you can tell them, oh, we're studying logs. What's a log? It's just an exponent. What exponent? Well, it's the exponent that you raise the base, whatever number is written here, unless there isn't one, in which case it's a 10. It's the exponent you raise the base to in order to get the value. This value is called the argument. Okay, but I'll call it the value. It's the value or the argument, right? So when you see this written, y equals log base 10 of 100, you can say, if I go 10 to the exponent y, I'm going to get 100. So that's a conversion from a logarithmic form to an exponential form, right? We just say, take the base, okay? I'm going to write it in because it's nice it's there. Take the base, raise it to this exponent, and this is the value that you get. Okay, so 10 to the y equals 100. Okay, whatever this base is. If it's 2, that would be 2 to the something equals the number, right? And now we can solve this, right? Because we just go back to the last unit and we say, well, 100 is 10 squared. Okay, my bases are the same, so what's the next line? Y equals 2. Okay. See that? I can pull it down a bit. Okay, so we see an expression written in logarithmic form, y equals log base 10 of 100. We convert that, you can just say, well, you can do a couple of things, right? You can convert it to exponential form and solve, or you can simply say 10 to the what gives me 100. And then everybody says 10 squared, right? So then you just say, well, then y equals 2, and I don't need to do this formally, right? I can just say y equals log 10 of 100. Now, you got your calculator out, hit the log key, and go 100 and hit enter. What do you expect to see? 2, right? All right, so what if we get y equals log base 10 of 10,000? What's y? 4, right? Because 10, so you're asking yourself, when you see this, right? When I see this, every time I see an expression written like that, I just say to myself, 10 to the what is 10,000? Okay, so this is what I say. I say 10 to the power what is 10,000? Okay, and the answer is, for this one, y equals 4. Now you could do this on your calculator. You just go log and 10,000. Hit enter and it says 4. Okay, so some of them we know, right? If the base, if the argument, this thing here, right? If the value or the argument is a power of the base, then we don't really need a calculator, right? We can just figure it out. Okay, or we can use a calculator. So if the argument's a power of the base, yeah, okay, 10 to the what? 10 to the 4. But what if I write y equals log base 10 of 500? You say, okay, wait, well 10 squared is how much? And 10 cubed is 1,000. So that means that y, 10 to the what is 500. It's got to be somewhere between 2 and 3. How do you find it? Use your calculator. So just go log 500. What do you get? 2.6. 2.69? Is that correct? Rounded to 2 decimals correctly? We say y equals 2.69. Okay, now go to your calculator and go 10 to the power of 2.69. What do you get? And it's not 500.
977788194.
Okay, but it's close, right? If we took more accuracy on this, we get more accurate.
Yeah.
If you go, do this again, go log 500, hit enter. Okay, and sitting there with the number, right? Now go 10 to the power of, and go second function answer to pull that number back in. And what do you get? Exactly 500, right? So the more decimals we give in this, the more accurate it'll be if we try and work backwards, right? Now most of the time, in real life when we're doing stuff, we can round off to a couple of decimals or 3 decimals or something like that. right? In that case, we're saying this is good enough. Okay? If we need exact, then we'll let the calculator use the exact 8 decimal places that it gives us. Okay, let's try this with a different. I don't even know. So there's going to be a new one now. Now I'm going to have to string them together. Okay. I didn't mean done. I meant new page. Y is equal to the log base 2 of 8. What's y? You can't use your calculator either, so ha. Okay, so what you may want to do is you want to say, I have an expression in logarithmic form. I want to write it in exponential form. So what's the base? 2. What's the exponent? Y. What's the argument or the value? Okay, 2 to the y is equal to 8, right? How do we express 8 as a power of 2? 2 cubed, right? So what's y? Y equals 3. Okay, so looking at this, I'm going to read that as 2 to the power of what is going to give me 8. And then I can sit there and go, well, 2, 4, 8, right? You sort of count on your fingers, 2, 4, 8. Okay, what if I go, y is equal to log base 2 of 1/2? Oh, let's make it more difficult. Let's go 1. Oh, you know what? Let's just, wow. Let's do 1/8. Log base 2 of 1/8. So 2 to the what gives me 1/8? Okay, so maybe I have to ask that right then. I'm going to say 2 to the what gives me 1/8. So when you read a log, when I read a log thing, what I'm really doing is I'm saying the equivalent exponential thing, right? Like 2 to the what gives me 1/8. That's how I read this, right? 2 to the power of y equals 1/8. Okay, so I can write it as exponential. Now we need to write 1/8. Well, okay, we know from just having done it that 8 is 2 cubed. Right? So it's 1 over 2 cubed. How do I get this out of the denominator? Make it negative. So 2 to the y is equal to 2 to the negative 3. What's y? Negative 3. Okay? So we may have to back up and solve an exponential, right? Which was generally not too poorly done on the, on the test. You're pretty good at 12 marks at the bottom type thing. Solving all of those. Right, and these are simple ones, right? Because they're the same base. The problem becomes if I get y equals log base 2 of 500, which isn't a power of 2. How are we going to evaluate that? Now we'll learn that. It's going to be a few days off. Okay. So right now we're sticking with numbers that are powers of the base. Okay. So while we're doing that, let's do this one. So let's say y is equal to the log base 1/3 of 27. Okay, so probably we want to convert that to exponential form, right? So what are we going to say to convert it to exponential form? 1/3. Where do I put the y? Okay, so if I'm going to do that, let's throw the 1/3 in brackets, right? Just make it clear that, so it's 1/3 to the power of y equals 27. Okay, how do we solve that? We need the same base, right? What's the base going to be? 3. What's 1/3? 3 to the negative 1, right? And 27 is 3 to the power of? 3. Okay. Just watch this. People are making mistakes like writing 9 as 3 to the 6th or something, right? Because 3 and 6 added up to 9, but that's not how it works. So just watch that you're getting your powers correct. And if you need to, just plug this into your calculator. Just go 3 to the power of 3, 20. Okay, good. Yeah, it's the right number. So we get 3 to the negative y is equal to 3 to the 3. So what can we say? So we could say that these two things are equal, right? So that negative y must equal 3. So what must y equal? Y equals negative 3. Okay. You want to verify that? You can't right now. Right? Because we don't know how to do a log base 1/3 on our calculator, but we'll learn that. Okay, we'll learn how to change to do that. Okay, but you can go 1/3 to the power of -3 and see what you get. Okay, so you can go back up here and throw in 1/3 to the power of -3 and see if you get 27. And if you do, then you know that you've done this correctly, right? You have found what? You found the y value, which is the exponent that we have to raise the base 1/3 to. 1/3 to this power will give you 27. Okay, so that is converting logarithmic form to exponential form. And then solving too, right? And some of the questions might just be convert from one form or multiple choice. When converted from logarithmic form, it's equivalent to A, B, C, D, or which of the following is it not equivalent to? That's sometimes the way we ask the questions, right? You've got 3 that will be equivalent and 1 that isn't, and you have to choose the one that isn't. Okay, so you just got to be careful when you're reading through the stuff. Which way is this thing going? Okay. Let's convert from exponential form to logarithmic form. So if I say 3 squared equals 9, that's written as an exponent in exponential form, right? If I want to convert that to logarithmic form, then what am I going to say? So what's the y value? 2. Okay, so in logarithmic form it's y equals, so 2 equals log base 3 of 9. Now, there's nothing to solve there, right? We're not solving. We're just changing the form, right? We're taking something that's written as an exponent, 3 squared equals 9, and writing it in logarithmic form, which says that the log base 3 of 9 is 2, right? Since 3 squared is 9. Okay, so the log base 3 of 9 is 2. Okay, let's try another one. Okay, in this case, 81 equals 10 to the y. And I just want to change its form. So what's it going to be? Written as a log. No, not 10, because what's 10? Is it the base, is it the log, is it the argument? Or is it a base exponent or a value? Yeah, y equals, right, because that's the exponent is y. Y equals log. Do I need to write a base? No, because it is base 10, right? I'm going to throw it in there just so that you can see that 10 there is the same as that 10 there, but just be aware that I don't have to write this 10, right? If I don't write this 10, then we all understand, oh, yeah, that's base 10. We're not solving this. We can, right? So if you had to solve this, right, what would we have done the other day? We would have graphed 10 to the y, and we would have graphed 81, and we would have found the intersect, right? This is, if I gave you 10 to the y is 81, on the exponent, if you're doing the exponents test or whatever, right, how would you do it? Well, I wouldn't do 10 to the y. I would graph 10 to the x, and I would graph 81 as y2, and I would find the intersect. How would you do that now? You say, hey, I can change this to be y equals log base 10, 81, which means I hit the log key, and 81, and enter, and I'm done. Right? I have my answer. Which is easier? Yeah, going log 81, obviously, right? Because you don't have to graph two things and then go and find an intersect. So it can be useful to be in logarithmic form if it's a common log. Or, how about we do one where we have 50 is equal to e to the y. Let's write that in logarithmic form. What's my exponent? Y. What's my base? E. How do we write a log base E? It's in front of the house and you mow it, or she has a morning talk show. Ln or ln, right? Okay, so that's a base e, and then what do we put in here? 50. Right. This is the same as writing log base e. Only thing is, we've got that ln key on our calculator, right? So if you have to find this, right, like what's y? Well, it's kind of like, I know that's almost 3. So, 3 squared is 9, 3 cubed is 27, 3 to the 4th is 81. So it's probably somewhere between 3 and 4. Well, what's the actual answer? What's the ln of 50? 3.91. Okay, so there we go, right? It's a value around where we sort of figured it might be. So we can solve these guys, right? If they are base 10 or base e, we can rewrite them into logarithmic form, or logarithmic form. It's not called logarithmic. We can write them as a log or an ln, a ln, a natural log, and we can evaluate this, right? Otherwise, what do, right? Well, I graph e to the x, and I graph 50, and I find the intersection. Okay, so now we know, hey, I don't have to do that stuff anymore, right? If I want to solve this kind of problem, if it has a base of 10 or a base of e, then I can change it from exponential form to logarithmic form and just enter it in my calculator and solve it. Okay, much easier thing to do, right? Okay, we did a bunch of that. Okay, let's just go evaluate a couple more logs. So if I say, let's just say I'm going to say evaluate. So it's just an expression, right? It's just like log 1/4 of 64. Evaluate. What is that? Anybody? Off the top of the head? Okay, so we got to start somewhere, right? So what we're saying is we need to find 1/4 to something. So I'm going to throw in a y. There wasn't a y there, right? But given this, I could write it as y is equal to, all right, and just say I want to find y. And to do that, I'm going to write in exponential form. So 1/4 to the y is equal to 64. Now, unfortunately, I mean, if this was base 10, life would be easy, right? You just go log 64 and, pull the number out of the calculator. It isn't. So we need to express these as powers of the same base, and that base is 4. So what's 1/4 expressed as a power of 4? -1, right? And then it's to the power y, right? What's 64 as a power of 4? 4 to the 3. So what do we get? 4 to the -y is equal to 4 to the 3. -y equals 3. Y equals -3. Okay. Now, how do you check that? You'd have to go back to here. You'd have to go 1/4, go bracket 1 divided by 4 bracket to the power of -3, hit enter, and you see 64, and you go, that's good, right? Things are going well here. Okay, so that's converting log form to exponential form and then solving. And how do we solve these? They need to be the base and the argument need to be powers of the same number, right? Need to be expressed as powers of the same number. And in this case, it doesn't necessarily have to be that they're powers of 4. We could express them as powers of 2. It would still work, right? As long as we can express them as powers of the same number, then we can solve these. Okay, what else do we got? Oh, log expressions. Let's try a couple of expressions. Which expression is greater? So log base 216 plus log base 2 of 2 for b, which is log base 2 of 1, don't need brackets there, 1/8. Okay, what do we have to do? Well, we have to evaluate them, right? We're going to figure out which one is the greater value, so we have to evaluate. Now, each one is a separate log expression. What is a log expression? Log base 216. What's a logarithm? It's an exponent, right? What's an exponent? Just a number. So log base 216 is just a number. Which is what? What is that number? 4? So I say 4? Okay. I just do fingers, right? 2, 4, 8, 16. Okay. Everybody cool with that, right? I mean, you're all, you know, I'm writing 4 and you're going, huh? Or no? You're all good? Okay. So when we say log base 216, we're saying 2 to the power of what gives me 16? Okay, so 2 to the power of 1 is 2, 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16. So, right? What's a logarithm? It's an exponent. What exponent? It's the exponent that we raise the base 2 to. I was using the base 2 with that. It's the exponent that we raise the base 2 to in order to get 16. Right? So we're saying 2 to the what is 16? 4. Because a logarithm is just an exponent, and an exponent is just a number, and so log base 216 is just a number. What's log base 2 of 2? Right, because 2 to the what gives me 2? 1. And that's equal to 5. Still? Or yeah, yes, no? Good? You keep it that way. Log base 2 of 1. 2 to the power of what gives me 1? Any base to the power of what gives me 1? 0. Right? That's a biggie. Okay, remember we looked at the graph, right? What did we say? The graph had one x-intercept of 1. Right? And that means that when the x value is 0, remember we're doing log of x, when the x value is 1, the y value is 0, right? Because the exponent that you raise any base to in order to get the value 1 is 0. That's just 0. What's log base 2 of 1/8? So 2 to the what gives me 1/8? We already did this, right? I mean, it's like flip back a page. -3, right? So how do you do that, right? Like, I mean, if you're just thinking about it, you just think of it this way, right? Okay, 2 to the 1 is 2, 2 to the 0 is 1, 2 to the -1, that's when we start getting into the fractions, right? 2 to the -1 is a half, -2 is 1 over 2 squared, -3 is 1 over 2 cubed. So this is 0 minus -3, which is 3. So this one here gives the larger value, right? Log base 216 plus log base 2 of 2 is greater than log base 2 of 1 minus log base 2 of 1/8. Okay? Blah, 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 blah. pH. So in chemistry, there's pH, right? So chemistry leads to pH. Is it a capital H? Yeah, pH. Which I believe stands for the power of hydrogen, right? And it's the hydrogen ion concentration. And I can say that without knowing what it means, although I'm sure 30 years ago I knew what that meant. Actually, I'm pretty sure I did, but I took chemistry as far as first year university. And all I remember is we were doing a lab and I stuck a pipette into my finger. There's the scar there. This is the glass thing. You're supposed to lubricate it before you put it in the rubber stopper. And I was like, ah, crap. So I just Started feeling a little faint, went to the sink, let it bleed out for a while, washed it with some soap, wrapped it up in a paper towel. Then I'm about to tell the instructor that I just broken a pipette and stuck it into my finger. So it's better to suffer. So the definition of pH is the negative log of X, where X is the hydrogen ion concentration, right? And what are low pHs? So as you go like 3, 2, 1, 0, they are acid and they get more acid, right? So like battery acid has a pH of 0. Don't spill it on yourself. It doesn't work. I have this shirt I used to like that's, oh, it's a t-shirt. It's got a whole bunch of holes. I was carrying the motorcycle battery like downstairs and, you know, it touched me and had acid on it. And it's like, why is my skin burning and why are there holes in my shirt? And the skin healed and the shirt didn't, so there's still holes in the shirt. That's battery acid, very acidic, right? How high does pH go? 14. Yeah, and 14 is, what's the other end of the scale? So acid, yeah, base or alkaline, right? Okay. So in chemistry, let's say the hydrogen ion concentration Now, if they're going to ask you a question on the diploma that deals with chem, there can be no assumption that you take in chem, right? They cannot assume that people don't have to take chem to graduate. So what they'll do is there'll be a little box like this which will explain stuff. It'll say the pH of the hydrogen ion, you know, blah, blah, and give you the formula. And then basically do this. Say the hydrogen ion, say, where here we say where X is the hydrogen ion concentration. Okay, so they say the hydrogen ion concentration of a solution is, and actually we use in moles per liter, right? That's not actually a capital L, is it? That's a mole. It's like 6.28 times something, isn't it? I don't know. It's all just numbers. A solution, the hydrogen concentration of a solution is 0.0001 moles per liter. What is its pH? Calculate the pH. All right, so really this is just a substitution into a formula, right? We're just going to substitute it, work it out. So we're going to say, okay, so P of X is equal to negative log 0.0001. And you work that out, right? So on your calculator, just go negative and then hit the log key and then go 0.0001 and you get 4. So the reason it strikes me now looking at this, the reason this is the negative log is these concentrations are very weak, right? Like they're always less than 0. And when you take the log of 0.0001, you get negative 4, right? Because 10 to the power of what gives you basically 1/10,000th, 10 to the negative 4. Now pH scale, we want to go from 0 to 14, so we got to flip that negative 4, so we stick a negative in front, it becomes 4, and we say this stuff is reasonably acidic, right? Like on the scale, because 7 is neutral, right? Like 7 is distilled water, and like 6 is saliva, which is a little bit acidic, and pH of 4 is tomato juice. Okay, so tomato juice has a pH of 4. Grapefruit or orange juice or pop takes you down to a pH of 3. They're kind of acidic. It's in your book. They got some lemon juice and vinegar are 2. Acid in your stomach is 1. Battery acid is 0. Don't drink battery acid. It doesn't go well in your stomach acid. And then the question we get. Here's the question we get. B. How much more acidic Almost. Is that cool here? Is it cool? Then I'm wearing shorts. And I'm old. Okay, so this is a common type of question in logs, right? It deals with things that have logarithmic scales, like earthquakes and sound pressure, i.e. decibels, and pH. And it's really saying, let's compare, how do these things compare? How much more acidic is a solution with a pH of 1.6 than one that has a pH of 2.5? So, we could, see, because what have we got? We got pH, right? We've got this value, and we would have to figure out this value, right, the x value. And then we could compare the two x values. So, I think we need more space, right? So we know that p of x is negative log x, okay? That's the solution. We're given 1.6. Okay, so here's what we're going to do with this. We're going to rewrite this in exponential form, right? So we're going to say, get rid of this negative first. So go negative 1.6 is equal to the log of x. Now, can you put that into exponential form? What's the base? 10. What's the exponent? So this x value is 10 to the negative 1.6. And similarly, we do the same thing for the pH of 2.5, right? Multiply, so it becomes negative 2.5 is equal to log x. And we write 10 to the negative 2.5 is equal to x. And to compare the two, ratio, right, we'll take 10 to the negative 1.6 divided by 10 to the negative 2.5. I'm dividing powers with the same base, so I subtract the exponent, so it'll be 10 to the negative 1.6 minus negative 2.5, which is 10 to the power of, I think it's 0.9, yeah. And what's 10 to the power of 0.9? Because this we can work out on our calculator. 7.943, blah, blah, blah. So a difference of 0.9 on the pH scale ranks out to a difference of 7 in how much more acidic something is, right? A difference of 1 on the pH scale is a factor of 10. So as you go from a pH of 2 to a pH of 1, it becomes 10 times more acidic. Not one time, right? But 10 times. And that's what a logarithmic scale does. And it covers an extraordinarily wide range, because a pH of 0, right? You put a 0 in here, becomes negative, it becomes negative 0, and it becomes 10 to the 0. You put a pH of 14, it becomes 10 to the 14th. So your concentration of hydrogen ion goes from 10 to the 0, which is 1, up to 10 to the 14th, which is in the hundreds of billions, right? Because 10 to the 9th is trillions. Okay. Now, problem is, we don't want to deal with something that goes on a scale from 1 to 100 trillion. So we say, hey, let's make it powers of 10, and now we deal with the scale that goes from 0 to 14. I'm subtracting. So when I divide powers with the same base, I subtract the exponent, so it's negative 1.6 minus negative. So I throw that in just so that I remember that it's minus and negative, which becomes a plus, and then we get that. Here's the easy way. Whenever you're comparing two things on a logarithmic scale, it's 10 to the power of the difference between the values on the log scale. So in pH, it's 10 to the power of the difference in the pHs. If it's Richter scale earthquakes, it's 10 to the power of the difference between the magnitudes of the earthquakes. Okay? So this is kind of the formal thing, which comes down to, it's really 10 to the power of negative 1.6 minus negative 2.5. Just take the difference between the two pHs and take 10 to that power. And there you go. You've got it. Okay, so key ideas in the book are on page 435. You want to be able to go logarithmic function to exponential function, convert back and forth. Make sure you're reading questions carefully.